I should give you, that's right. It's my great pleasure to introduce to you our speaker for today, Professor Harry Atwater from Division of Engineering, Applied Physics and Material Science. Harry got his full education at MIT in the 80s, doing his bachelor's, his master's, and then PhD in electrical engineering. He immediately moved to Caltech, and he's really, like one of the early generators of the whole fields of nanophotonics and plasmonics. And I think looking at the sub-wavelength scale to really figure out how energy flows, and the fact that it's not just material science, but it has to do with geometry and a lot of subtleties. Personally, I've gotten a lot of, I'm a very selfish person, so I got a lot of useful advice from him over the years when we were trying to explore ideas for the LIGO mirror coatings, and specifically when we were looking for doing cryogenic optics. And he's an expert in all things silicon, as I found out. He's also the director for the Joint Center for Artificial Photosynthesis, and then also the DOE-funded Liquid Sunlight Alliance. And he's the EAS division chair since 2021. I think, how many of you people out here have seen the television show Ted Lasso? Have you? I know one of Harry's passions is also coaching soccer. I don't know, have you seen the show?
Yeah.
Yeah. So I just thought it was a great thing that he's a soccer coach, because anyone who's coached soccer kind of knows that it's an early track to learn how to manage faculty, maybe. And I think that's one of the reasons he's been such a successful division chair over the years. So he's involved in a number of research projects of which I'm deeply interested, but I hesitated to ask him about this one. So I'm glad that this was his topic of that he wanted to tell you about today. So he's here to tell you about this really exciting breakthrough Starshot project. Back to you, Harry.
Okay, thanks, Rana. Yeah. I'm happy to be able to have the chance to talk to you about Starshot today. The goal here is really to tell you about this project, which you may have heard about through other sources. It began approximately 10 years ago. And you may wonder, well, whatever happened to breakthrough Starshot? What's going on? And so this is really an update on what sort of the first era or epoch of research. So I'm going to tell you about things that we've done in our group, but also more broadly about the Starshot project as a whole from the first phase of the research. And as an electrical engineer and humble observer of the world of science, to me, I found, and this is not surprising to those of you who are astronomers, this to be a very compelling sort of way to view the relationship between our sun and its nearest star, which is to look at the logarithmic scale in terms of distances between our solar system, the interstellar medium, and the nearest stars. And the nearest star system is the Centauri system with Alpha and Proxima Centauri, Alpha Centauri A and Alpha Centauri B. And of course, we know that since the beginning of the space program, essentially only 5 probes have ever left the solar system. And the ones that are going fastest and longest, of course, are Voyager 1 and 2, which have gone just beyond the heliopause. And they're about 23 light hours from the Earth right now. But the distance to Alpha Centauri is 4.2 light years. And at the speed of the travel of the Voyager spacecraft, it would take about 70,000 years to reach Alpha Centauri. So for any kind of project, an academic project, that's if you measure this in terms of graduate student careers, that tests the patience of the most patient graduate student. And so the real problem, of course, is the sobering calculus of the rocket equation that is really limiting the speed of chemical propulsion, both through Newton's laws and just the relationship between mass and velocity. So the speed of chemically propelled spacecraft is in the range of 1 to say 20 kilometers per second. If you add an ion engine, you can get a higher ejection velocity for the fuel up to and get to about 30 kilometers per second. And the fastest spacecraft are really in that range, and that doesn't change the time scale. And so really the best fuel from the point of view of efficiency of time is light itself. But of course we know that light is a very gentle means of propulsion. And so if we think about the momentum transfer of light, it's proportional to the intensity. And this governing equation right here in the, let me see if I can get the laser pointer without getting something else. There we go. This governing equation is an expression of the velocity in terms of the incident power and the size of the aperture that's being propelled by radiation pressure and the wavelength. And the mass sits in the denominator to the 1/4 power. So it's actually a fairly gentle dependence on mass. But if you want to go very fast, that means essentially you need to have very high power density, about 1 megawatt per square centimeter. Incidentally, that's not a particularly high optical power density. We go to gigawatt per square centimeter in the lab to excite nonlinear excitations in materials, but it still is pretty high. So at a wavelength of a micron and with a mass of a gram at that power density, this governing equation tells you that it would be possible to get, after an impulse of acceleration of about 1,000 seconds, up to 20% of the light speed. So which would enable a journey to Proxima B, which is, I'll talk to you about is the target that is interesting from this viewpoint. And this is an idea that actually is almost as old as the laser itself. One of the first proponents of the idea of radiation pressure driven spacecraft was this fellow Robert Forward, and Forward was a colleague. He was in the same aisle at the Hughes research lab in Malibu in the early 1960s as Ted Maiman, who was the inventor of the ruby laser, following the discovery of the maser by Charles Townes. So this really is a sort of an old enterprise, and many ideas around this were developed as sort of what you might think of as sort of wild and crazy ideas, but nonetheless things that didn't stretch reality, at least in terms of the fundamental physics. One of the most comprehensive sort of additions to this set of ideas was from Phil Lubin. I think Phil came here maybe a few years ago and gave a talk to the physics colloquium. So he developed what he called a roadmap to interstellar flight. This was published in 2016, and basically is a comprehensive analysis of what would be needed to do radiation pressure driven propulsion of a spacecraft in terms of the governing equations, the design, and some preliminary ideas around the optics and so forth. So this year, 2016, was a very interesting year. This was the year also that this paper was published, which, as those of you who are astronomers will recognize, was the discovery of a exoplanet that looked to be in the habitable zone of Proxima B, one of the stars in the Alpha Centauri system. So essentially would constitute the closest planet to the Earth. And therefore, that really sort of, these two developments together, the idea that we could build a laser-propelled spacecraft and that there might be an interesting candidate within a couple of, among the star systems that are closest to the Earth, ramped up the enthusiasm. The enthusiasm was fueled by this group of people who, in a somewhat gauzy press conference at the top of the World Trade Center in April of 2016. So you can see Stephen Hawking sitting in the front there, and Freeman Dyson standing in the back. The person next to Freeman is Yuri Milner. He was the patron of the Breakthrough Starshot. Of course, he's the patron of the Breakthrough Physics Prizes. And this program was launched with enthusiasm by this group. And the basic idea is to develop an Earth-based laser array that could produce this megawatt per square centimeter beam for propulsion, for radiation pressure propulsion, and to do a flyby, crucially within the remaining lifetime of Yuri Milner. 20 years corresponds. Yuri's in pretty good health, so that seems like a feasible idea. So that would require then a point design for this mission using the governing equation that I showed you of a final velocity at about 20% of the light speed. And that requires a light sail of about 10 square meters with a mass of 1 gram. Okay, so that's a pretty demanding standard, and we'll talk a little bit about that. So light, of course, imparts very little in the way of momentum. So if you imagine pointing a laser, like my laser pointer here at the screen, if I pointed this at something that had the mass of a thumbtack continuously for a week and the battery held up, I would be able to accelerate that thumbtack on a frictionless surface to about 1 millimeter per second. So that gives you an idea of the scale. So that, if we now apply the same sort of governing relationship, so that says that at a megawatt per square centimeter for this 10 square meter sail, we would need about a 50 gigawatt laser array at a wavelength of 1 micron. That we can talk about the choice of the wavelength if you like. And it requires quite a large laser aperture. That would be the largest laser system ever built. So this was a really exciting idea. When I first heard about it, I thought it was totally absurd. But Pete Worden and Pete Klupar from the Breakthrough Foundation came to visit me, and they said, Yuri Milner would like to talk to you about some of the issues related to materials. So I went over in about November of 2016 in the Beverly Hills Hotel, and I spent about 3.5 hours sitting in the courtyard of the Beverly Hills Hotel talking with Yuri about the light sail mission and the role that materials would play. And I guess at the end of it, he thought that was an interesting idea, because we started then the work on the phase 1 of the research program that I'll tell you about today. So of course, momentum transfer results in radiation pressure that's proportional to the reflectance plus the absorbance of the material. And it turns out that in this case, because we're using radiation pressure to propel something through space, we really have to pay close attention to absorption, because the only mechanism in space for managing the thermal load is through radiative emission. And that's going to dictate that the absorption be as low as possible. So there's some very interesting dynamics. So you might think of these as optomechanics issues for laser-driven light sails. One is making sure that the reflectance is high enough. The reflectance doesn't have to be within, parts per billion of unity. It actually, any reflectance between, say, 80 and 100% would be fine in terms of energy efficiency. The real issue has to do with absorption and thermal engineering. But one of the ones that arose, the issues that arose as being really a challenging one to deal with, is the stability of the light sail, the dynamical stability. If you now take a weakly focused Gaussian beam, as I've indicated here schematically, a weakly focused Gaussian beam impinging on a flat surface that's a finite extent, you can show that will create a dynamically unstable propulsion trajectory. You will not be able to propel that stably along the optical axis. So you could use some higher order beam. People proposed using donut beams and shaped sails and all sorts of things. But that turns out to be a big challenge. So we spent quite a bit of time thinking about how to design something that could exhibit beam riding stability. In other words, if it had some instability, it could self-correct and actually maintain a metastable trajectory along the optical axis. And then, of course, because we have something that's 10 square meters in size and it weighs 1 gram, that means the nominal thickness of this structure has to be something like a few hundred nanometers. And that means we have a membrane. We don't have something that's a rigid body. If I have something that's a few microns in size, if it's a few hundred nanometers thick, it's rigid. But by the time it gets to be something like tens of microns to 1 millimeter in size, then it becomes flexible. And so you have to think about the shape stability as well. So I have always been really excited and interested in the way that we can use nanoscale structures and nanoscale light matter interactions to control the scattering of light and the properties of materials. And so there are many different sort of schemes and tools in our tool chest that we can draw upon. The one that you're probably most familiar with is optical tweezers. And in optical tweezers, we can trap small dielectric objects of the order of the wavelength or smaller by using a strongly focused beam with a high numerical aperture objective. And in that case, what's happening is you're generating a trapping potential that's arising from the gradient force in the beam itself. So on the other hand, and so that's very nice. That's a nice way of trapping, for example, an isotropic dipole-like dielectric object. But suppose we have a weakly focused Gaussian beam, or if we have a large object, we can't impose a large gradient force because the beam necessarily has to spread out and interact with the entire object. So if you have something that's millimeters to meters in size. So in that case, we actually have to encode the optical forces on the material itself. Okay, the simplest idea for doing that is to use a diffraction grating, but a sort of generalization of that we appreciate in nanophotonics is that we can develop resonant or non-resonant metastructures that allow us to control the entire angular dispersion of light scattering. So you can do that in many interesting ways. We can pattern structures on a surface that allow gradient forces to be developed that would suspend and trap an object. We can even do things like produce, by interfering two beams, produce a force that is anti-parallel to the wave vector. So you can actually build the thing you saw in Star Trek, which is a tractor beam, something that can pull with radiation pressure as well as push. So, but when we work with large objects, then we have to start thinking about many more sort of physical aspects than when you're trapping a small particle with a strongly focused beam and the optical tweezers kind of application. So we have a large object. In this case, that object will have a dielectric properties, complex dielectric function, and a macroscopic shape that we have to cope with. It's, of course, flexible. I mean, it's a membrane. And so we really have to think about it on many length scales. And we have to think not only about the electromagnetic field interactions as with the small particle. The particle itself is rigid, so you don't have to really think that much about the deformation of the particle. But we need to think about the mechanical modes and the excitation of the structure itself, and then also the body dynamics so it really brings together mechanics and electromagnetic theory together. So how do we grab a hold of this and try to do some experiments that can tell us something about these ideas? And really the aim of this research effort that we began in 2018 was to identify showstoppers. Is there something that fundamentally tells us that this is nonsensical or infeasible? And so to do that, we wanted to really sort of test some simple ideas related to the dynamics and the forces that could be applied. And so we needed a way to translate the ideas that had been developed by this group from Breakthrough Foundation around design of an interstellar light sail to thinking about how that would manifest in terms of a freely accelerated structure that's more idealized. And then really, in order to start experiments that we could carry out in a simple fashion in the laboratory, we wanted to work with suspended structures because we can learn an awful lot about that, and they're a lot easier to handle than freely levitated or accelerated structures. So in 2018, we began a research program, phase 1 research program. So the aim was to learn what would either enable or prevent a light sail spacecraft, and then also things related to the photon engine, the phased array laser system, and a communication system. So none of this, of course, exists or did exist at that time. But the question is, could you conjure up ideas that would either enable or prevent those things from being possible? So we aim to develop scientific principles, develop some design concepts, and also create a community of scientific research. And so this is the group of people that got involved. So people from these various institutions around the world, mostly at academic institutions and a couple of small companies that participated in the work. And so what I want to do is to leave you with some thoughts about the accomplishments. And so some of the things that we did in this research program over the last 6 or 7 years or so is to identify feasible materials, to identify designs for stable and efficient propulsion, and to also develop simulation tools that could help us build more complex structures to understand the dynamics. And this group of researchers that I showed you the logos for began work on many of the issues: how to build thin membranes that could have high reflectivity, to make measurements, develop designs, to study the thermal response of these things under these very high power densities in thin membranes. So at Caltech, some of the things that we did was to develop essentially a material selection sort of analysis for materials, to look at the issues, the first order issues related to thermal balance between propulsion, absorption, and radiative emission to develop a steady state temperature, to develop ideas that would allow us to self-stabilize these light structures using metagrading structures. I'll tell you about that. We did some optical characterization and then study of the membrane behavior of these thin membranes. So with regard to materials, very similar to the issues that people like Rana face with the mirrors and LIGO, we're interested in working with materials that have extremely low absorption coefficients. In this case, because of the need to accelerate the light sail kinematically, we're interested in something that has a reasonable mass density. And then in order to get good reflectivity, you like to have a material that has adequate refractive index. We can use photonic design to compensate for that to some extent, but just the index contrast between vacuum and the material itself generates a significant advantage in terms of generating high reflectivity materials. So this is sort of a suite of materials that were considered. Most of them are ceramic or dielectric or semiconducting materials. And out of this sort of thinking about all these possibilities, we wanted to consider what materials could be scaled up to meter scale or tens of meter scale structures. And from that emerged silicon nitride as a material candidate. That's sort of our number one. So I guess our self-imposed mandate was like the British monarchy to present an heir and a spare. We wanted to have one good material candidate and then a second backup in case it didn't work very well. So our second backup was working with 2D materials like molybdenum disulfide, which has the material characteristics, but it looks like it's going to be, at least now, probably hard to scale materials in the same way as with silicon nitride. So silicon nitride, serendipitously, has been used for all kinds of scientific applications. Now it's used in low-loss waveguide photonic circuits. That wasn't true at the beginning, but it's used in cavity optomechanics, mechanical resonators. And so there was a lot of knowledge base. And of course, silicon nitride is something you can deposit on whatever this, the largest size substrate you can make in a clean room. So that's another big advantage. It has a scaling advantage. So I want to say a little bit about beam riding stability. And to study beam riding stability, we developed a multi-physics simulation that takes into account absorption, reflection, scattering, and nanophotonic resonances. And of course, what we're interested in is materials that are thin membranes. And so if we simply illuminate, for example, the structure that I just showed you, or this flat structure, you can see what happens is it becomes shape unstable, and it's also beam riding unstable. It sort of veers off the optical axis. So if you use something like a parabola, you can show that a parabola, if it could maintain its shape, would be have beam riding stability, but a thin membrane parabola, even if you could imagine making it, can undergo deformation unless you rotate it. If you rotate it, the stability gets a little bit better, but ultimately this one wasn't rotated fast enough, so it meets the same fate. If you rotate fast enough, you can stabilize this membrane. Essentially what you're doing is trying to rotate at a speed such that the tensile strength or the tensile forces, stresses on the material don't exceed the tensile yield strength of your material. So typically if you have structures that are tens of square meters in size, if they're rotating something like 10 to 100 RPM, that is below that tensile limit. But of course, the things I showed you on this last slide were ones where we had exotic shapes, like we were imagining that we're going to build a parabola that's somehow meters in size, and it has exactly the parabolic shape, has a beam riding stable structure. Of course, the simplest things to make are flat structures, but flat structures that are specular reflectors exhibit this instability. But if we build structures that have metagratings, or any sort of grating will do, but metagratings now have the property that we can control the number of diffracted orders. We can either scatter the zero order beam or just plus and minus one. And in particular, what we can do is develop relationships between the transverse force or the torque. So the transverse force is the one that is pushing the light sail back onto the optical axis. The torque is the term that is now turning the light sail back onto a trajectory that's perpendicular to the optical axis. So these in-plane force versus angle and torque versus angle curves are the ones that can give rise to a stabilized trajectory. So we developed for thin membranes that are spinning at tens of RPMs, that stabilizes a flat structure. The flat structure, if it were specular, would be unstable, but with metagratings, and this is a full wave simulation that allows us to look at the forces imparted by the metagrating structures, and this was worked out in this paper, we can stabilize and propel a flat structure. So that enormously simplifies the job of making a light sail and having some assurance that you could propel it in a stable fashion. So now we're also interested in the some of the mechanical dynamics. So we have a thin membrane, and we're propelling it along an optical axis. The membrane itself is not a rigid structure. If it's large, it has its own modes. It can have and in this case, in our laboratory this is our E. coli, or our mouse vector, so to speak, for optomechanics. It's a thin light sail membrane that's held on ligaments that are highly compliant, and they're attached to a rigid frame. It's a silicon frame. And that allows us to now measure the dynamics and then track this easily in the lab. It allows us to now, and we actually got to learn a number of very interesting things about the in-plane and out-of-plane modes, torsion, and translation. So if we now excite well below the mechanical resonance frequency, we excite this with a radiation pressure so-called quasi-statically. We're pushing on it, and we're applying an AC modulated signal, but it's way below the fundamental resonant frequency. So then this little light sail structure, which is tens of microns in size, that allows us to do experiments with ordinary laboratory sort of watt scale lasers. We don't need to have kilowatt or megawatt lasers in the lab to do the experiment, but we can study the dynamics. And so in this case, we have just a damped harmonic oscillator. We could easily find the resonance frequency and determine the quasi-static dynamics. So it's very similar to just statically pushing on an object if you're far away from the resonant frequency. In other words, you don't see any significant phase shift. And to analyze this, we built up a characterization platform that includes the oscillator itself, and then something that can allow us to make very sensitive measurements of displacement, and then also to look at the change in the resonant frequency, which is due to the change in the properties of the materials due to either linear or nonlinear changes in the materials properties. So the resonators themselves look like this. And they're analyzed using a structure called a common path interferometer. This is a interferometer that has a reference beam and a probe beam. And as any experimentalist knows, everything in the lab vibrates. And we want to make measurements that are with picometer resolution. And we actually are mechanical resolution that's attributable from this common path interferometer is about 10 picometers. What we do is we now reference this to this is a rigid silicon frame. So we can, and it's of course moving in, because the ultra vacuum system in the lab is moving. It's whatever the speed the floor is moving and so forth. But we can now, by unfolding the displacement, and we can determine, unfolding these oscillations, we can determine the harmonic displacements of the light sail itself with something in the range of 5 to 10 picometer resolution. And the neat thing about this is that we can now probe with effectively a diffraction limited beam spot with this kind of displacement resolution out of plane. So the other thing that we learned is that silicon nitride is a low loss material, but its loss is not zero. It's in the 10 to the minus 4 range or so. And if you crank up the power, you will see some change that induces heating that changes the compliance of the material itself. And those springs that are springy and therefore compliant, they become more compliant, and we see a change in the mechanical frequency. So in essence, what that means is the change in the resonant frequency is a very precise bolometer. It's a power measurement to tell us exactly how much optical power was deposited in the sample. Of course, we think we know the incident optical power and we think we know the reflectance, but this has turned out to be a very precise measurement of the actual power dissipated in the material and reflected. So we can also now, what we're interested in doing is measuring the force due to radiation pressure. And in this case, in order to measure the force, from Hooke's law, I need to know the spring constant and the displacement. So I figured out the displacement, but how do I measure the spring constant? Well, I can use the equipartition theorem. And if I know the temperature of this thing in steady state, I can actually determine, and I know its displacement, I can determine its spring constant. And from that, I can go back and resolve the force directly. So I'm using two independent measurements to actually directly measure the force. So we also were able to look at the torsional modes. And in the case of a torsional mode, we use one of these small diffraction limited spots as an excitation beam, and then another one as a probe beam. So this is the common path interferometer probe that has about a spot size of a micron or so. And now, of course, if I probe off the centroid, or if I pump off the centroid of this structure, I'm going to induce torsional oscillations. And that can give rise to higher order modes that I can see. And I can see, if I can map out these higher order modes of this oscillation. So I'm now learning something about the properties of this membrane itself and all of its body dynamics. So everything I told you so far was about out of plane motion, but I'm interested also in learning how much the in plane motion, what's the in plane motion in response to the structures that I've created. But fortunately, the metagratings themselves also can be used to create an interferogram that produces a displacement dependent interferometric measurement. And so we can actually use that in this reflection configuration to determine with a precision of about 5 nanometers the position in the lateral direction. So we know now, so we have about 5 to 10 picometers resolution out of plane and then 5 to 10 nanometers in plane. So now we can, we were able to determine the dynamics of the light sail in this case. So what happens, everything I told you so far was about excitation far off the resonance at low frequencies. These resonators have resonances typically in the range of 10 to about 50 kilohertz, and they're quite unusual resonators. Most resonators that have frequencies that high are pretty rigid, pretty stiff, but because of these springs, we also have a very compliant structure that has quite a high quality factor. So if I excite at resonance, then I get a now displacement amplitude that is increased by approximately the quality factor. So the question is, what happens to this structure if I displace it now at resonance? And so at resonance, I can see large displacements, and well, I'll have beam elongation. There'll be nonlinearities that will come in from purely mechanical reasons that give rise to changes in the resonance frequency. And so that gives rise to bistable and nonlinear excitations. We have so-called duffing oscillations. So our forced damp harmonic oscillator now has, in addition, it has a cubic dependence here on displacement. And then there are two modes. There's a high amplitude and a low amplitude solution. And if I excite this at resonance, I now change the excitation frequency from being the right at the mechanical resonant frequency. I can drag, so to speak, the forced oscillation off its resonance frequency until it lets go, snaps back, and recovers into this low amplitude solution. And so that represents a bistable trajectory that we can see. So one of the interesting things that came out of that is we found that when we excite on resonance, we could see sidebands here that are excited. These sidebands actually, in principle, should be excited by noise. As we crank up the laser power, we can see them quite prominently. And another very interesting aspect arose when we were performed driving in a duffing oscillation regime. So we're now dragging the oscillator off its resonance frequency. But now we also excited at a probe excitation at a frequency where one of these sidebands appears. And we actually, in this case, instead of using another optical beam, we just used a piezo oscillator, just an audio oscillator. It made a huge racket in the lab, and only the people doing the experiment ever wanted to go in the lab. But it had some, and of course that's a nice thing because you can all that acoustic vibration is transmitted through the ultra-vacuum system and picked up by the sample. So in that case, you actually excite an entire mechanical frequency cone. So it's quite interesting. That was quite a surprise. We didn't expect to see that. So this is a very interesting oscillator. It's a structure that has quite high compliance, quite large displacement, but quite high Q. So it has some interesting properties. So and that leads to some very interesting phenomena that we saw. If you now sort of cast the motion into a rotating frame, and you can look at the dynamics as a function of the two quadrature elements, what you see is that there are two stable solutions, this high amplitude and low amplitude solution, and there's a so-called separatrix, a boundary a stability boundary between these two. Between those two solutions. And as you drive harder, you actually expand the high amplitude phase space within this for these two motional quadratures. And we can see that, and we're able to see map out the resonance and the sideband frequencies and ultimately the excitation of these frequency combs for these structures. So an interesting implication is now coming back to materials. So Rana cast me as someone who knows about materials. But so let's imagine that this oscillator, you sort of abstract everything away and you say, let's treat this as though it were a material, and ask myself, what's the nonlinear optical coefficient? What's the N2 or the chi3 of this material that I just created? And in that case, you can do this analysis by saying, let's imagine the oscillator itself here being displaced on its springs produces a phase shift that's proportional to its displacement out of plane. Then you can see a mechanical responsivity that gives rise to the displacement, but the force is proportional to the area. So now this is unusual. That mostly with materials, the nonlinear optical coefficient, like the Kerr coefficient or the Pockels coefficient, or due to multi-carrier absorption. These are properties of the material, but here now this is proportional to an extensive property, which is the area. So for our little oscillators that are about 20 or 30 microns on a side, the attributable nonlinear index is among the highest of any material you can make by chemistry or physical methods. It's orders of magnitude larger than the Kerr, N2 nonlinear index coming from the Kerr effect. So we think this could be quite interesting in applications where people are interested in inducing large non-optical linearities, like developing optical neural networks and things like that. So let me tell you a little bit about the story of the analysis of the not only the lightsail, but some of the other things related to the Starshot project. So one of the sort of ambitious imaginations is that we're going to build a photon engine. That's what the terminology for this phased array laser is. It's an engine that drives the spacecraft. And so this is, sort of epic proportions, of course. It's hundreds of gigawatts power, and it's hundreds of meters to kilometers in size. So we did an analysis to say, well, okay, let's imagine we have the components that we have today, solid state lasers or fiber lasers. How would you actually do this? Imagine budgets are not an issue. You have something like the budget for CERN or, LHC or something like that. At one point, Yuri Milner was entertaining the idea of seeding the work to do something like this. And so we did an analysis of this, and the technical analysis centered on some of the properties of solid-state lasers. And I was just talking with Rana before the seminar. There's been spectacular progress. It's not really, I think, made big headlines. This is work done by the group of Susumu Noda at Kyoto University. He has, so one of the issues when you make a laser bigger, so to make a laser have higher power, you want to make it bigger, and because you're more power per unit area, or the constant power per unit area, you need more power, you need to make it bigger. But one of the issues is when you do that, it becomes multi-mode. So he managed to develop a photonic crystal laser that is hundreds of microns in size in aperture that lasers in a single mode with a power of 50 watts. So it's really quite a remarkable laser. It's a very high beam quality, very narrow line width, very narrow divergence. And it's the basis for the laser elements in this dense laser array that we developed as a design for Starshot. They use these photonic crystal lasers and disperse the beam so we have relatively uniform illumination. And of course, when you build a phased array, electrical engineers talk about something called the sparse array curse. If you have a dense array of phased radiators, you can form a beam that has a shape and a directivity as you like. If you have a sparse array, you end up with spurious side lobes that you can't really control. And so it's really important that you have a design concept that could present itself as a dense array. And so this appears to be one that could generate a dense array. So importantly, if you have billions of elements, you have to think about how you synchronize the excitation of all these elements at once. So we actually worked with a group at Australian National University that did a conceptual design and then also a breadboard for a few dozen lasers of how you would use a single seed laser. This is very much like the way the NIF laser at Livermore works. A tiny little solid-state laser seeds the entire petawatt laser there. And similarly, they developed a scheme for using a single seed laser to now enable the pumping in a phase coherent fashion of up to 100 million radiators. Also, there's the issue of communications. If you want to send a spacecraft out into the interstellar space or to a nearby star, you would like to send a signal back. So what are the issues associated with that? So in 2019 and 2020, a group was formed to study optical communications and what are the sort of the gaps in knowledge and gaps in physics that would enable or prevent communications of a signal. And it was, after a short amount of thinking, it was sort of regarded that the only feasible wavelength range is optical. And this is also, I think, very synergistic and informed by the work led by NASA on deep space optical communication as an alternative to spacecraft communication with RF apertures. We have a very distinguished group here at JPL that's working on that, that developed the optics for the Psyche spacecraft, and which has now been the spacecraft that has developed a actual prototype demonstration of deep space optical communication. So this was used as the baseline, the performance of the deep space optical communication system on Psyche. And the question is, how many orders of magnitude in gap is there between what's possible today with Psyche and what would be needed for transmitting an optical signal back across 4.2 light years? And that gap is approximately 7 orders of magnitude. And so with the signal processing people thought that by encoding multiple bits per photon, we could recover maybe 1 or 2 orders of magnitude. But the biggest gap is in the collection area for the detectors. So then this turns into a question of, how many detectors do you need? The beam coming back to Earth would be approximately the size of the Earth itself. So you can put detectors wherever you like, and the more the better. And that really implies that you need to have something that would be low cost. And this low-cost telescope was designed, and it's really based on a design that originated with Professor Roger Angel at University of Arizona, who developed this low-cost telescope using active adaptive optics, thin-film adaptive optics. And the aim here is to make a optical aperture that's meters to tens of meters in size, instead of costing millions of dollars, to cost maybe a few thousand or $10,000. And so that was the sort of budget. And this is the design that was, and this is the size of the array that you would need multiplied by 50 to recover those 4 to 5 orders of magnitude. So, okay, that's a large number of receivers. Each one of those is something like $5,000 to $20,000. But it's not out of the realm of, it's not out of the realm of possibility or feasibility. The other thing to note about this is it doesn't require, this is not imaging. These are just an array of light buckets. So the collection in each bucket, each detector can be incoherent. We're really just interested in counting photons. So what about the spacecraft itself? A lot of, what would the spacecraft that actually would be capable of flying to Alpha Centauri look like? And nobody had really taken a serious sort of design approach to that. So we thought that would be an interesting project. And based on everything that we had learned from the dynamics, this is what we came up with as a sort of first cut design. So this is a structure that meets the so-called point design for the Point 2C mission. It has an area of, it has a diameter here of 4 meters, and a mass of, a sail mass of 1.5 grams with a payload mass of about 1 gram also. So that means it made of silicon nitride about 200 to 300 nanometers thick. And so what's depicted here are instruments. I won't go into all the details of the instruments, but they include onboard magnetometers, a flat, a phased array, an optical phased array for forming the communication signal, for communications aperture, power. Let me just mention something about the power. Okay, so this is the thermal radiator. So one of the issues, of course, is to keep all the instruments that you would embed into the fabric of this sail cool enough to maintain their operation after the end of the acceleration impulse. And so some laminate designs using these photonic crystal kind of motifs allow us to simultaneously achieve the thermal and reflectivity requirements for the light sail. So there was a power and energy working group that studied the issue of how much power and energy is required to return the data. And if you set an objective of returning 100 kilobits of data, then and you set, and of course power is required for other things as well, pointing and computation and so forth. The sail itself, after the acceleration impulse, is a kinematically flying object. And so we imagine using radiation pressure coming from light sources on the sail itself to gently steer the beam, or steer the light sail. But it's really flying kinematically. So in order to meet this communication and power budget, we need an energy of about 14 kilojoules. The steady state trickle power is about 20 microwatts, and when you turn on all the instruments to point a laser phased array system back at the Earth, you need about a watt of peak power. And so this is a design for a thin film radioisotope thermoelectric generator that you can make, and this would be locally hundreds of nanometers to a micron thick, so perhaps adding a little bit to the mass, but locally where the generator is. And so the idea is you put your hot radioisotope source here. These thermoelectric elements produce thermal gradients that produce the power. So this is something that was demonstrated during the time of our project. So, okay, I sort of have told you a story about an audacious idea to go to Alpha Centauri and to explore and have a look at planets around another star. What could be done before you get there? So if you use the governing equation and the nomograms that Phil Lubin first drew to analyze how you would translate from the parameters for the Starshot mission at 20% of the light speed with a megawatt per square centimeter power density and a 10 square meter sail. And imagine you now were to ask, let's set as a design objective something that simply goes faster than Voyager. So then the sail radius drops dramatically down to less than a meter, and the powers required may be in the hundreds of kilowatts to megawatt range. And those are actually similar to lasers that already are being built today for both defense and commercial applications like laser cutting. These are devices, for example, fiber lasers that are becoming available today. So we also looked at some of the questions of what would be the actual sort of structure of a mission that would explore a destination within the solar system. And then we asked, what would the size of the structure look like? What speed would it go at? What would its payload size? And so using all these governing equations, we could conjure a design that would include about a 10-gram payload, so for instruments, and allow for a sail area and a velocity here of 100 AU per year. So that's faster than any chemically propelled spacecraft. It's faster than solar sails that would, so-called sundiver solar sails that would go close to the sun. And the price tag for that, using the cost of today's lasers, and in fact, it's the cost of the lasers that ultimately, and the laser system that ultimately completely overwhelmingly dominate the cost of building a Starshot-like system, would be about $300 million. So is $300 million a lot of money? Yes. But that's about the price of what's called a mid-scale mission by NASA. So it's not a preposterous sum of money. So I think it's kind of interesting to think about that. The energy costs are, it's a few $100,000 worth of energy. The sail, we imagine, would be about $1 million to build for each sail. So it's not a crazy idea from the economic point of view, at least to get started with this. To go to the ultimate aperture that's a kilometer in size really is going to be dependent on a drop in the cost per watt of lasers. And so we were just talking earlier about many of the things, maybe inertial confinement fusion that could be enabled by a dropping cost of lasers. And such lasers are now in the range of somewhere between 10 cents and $1 a watt. They need to get down to about a penny a watt before something like this would become feasible. Finally, you can ask the question, is this even worth it? I could, astronomers will say, I can learn as much as I need to know from Earth-based observations or telescopes in the near-Earth region. I can study planetary transits. I can look at the wobble induced by planets. around stars. I can learn a lot about possible remote worlds. So I think to that I would say it's interesting to ponder the images of Pluto that were taken with near-Earth observation on the right, and then from the New Horizons spacecraft. And I guess it would be an interesting, you have to ask yourself, did I learn something more from this image of Pluto than I knew before from an Earth-based observation? And another way it's interesting to think about that is imagine we had a Starshot lightsail approaching the Earth at 20% of the light speed. And so if you were 2 hours away from encounter at 20% of the light speed, and there was just about 3 AU, this is the sort of image you would see with a typical optical aperture. As you get down to about 1.4 AU, about an hour away, this is what you see. And now when you get to close encounter, this is what you would see. You would see the entire blue marble. And I submit that you learn a lot more about the Earth when you see that image on the right than you do the other two on the left. And so really the only hope of seeing those kinds of images of planets is to go there. So I want to say thank you to the students and postdocs, a very talented team over about a 10-year period, many of whom are now elsewhere in other academic locations, who contributed significantly. Most recently, a PhD student, Ramon Gao, and Lior McKelly, who carried out some of the work that I told you about today. And then I guess I'll leave you with some ideas that came out of at least my thinking about this, which is that the technologies that would be required to develop a laser-driven light sail are, in my estimation, sort of inevitable technologies. Lasers and dielectric materials, things that we make at massive scale, which are following Moore's law curves. It seems to me that it won't be more than a few decades before these things become, orders of magnitude less expensive and more, ubiquitous than they are even now. Some of the first missions could be in or near the solar system. And so I think an interesting thing I'd like to start a conversation is about the most promising science cases that you could imagine to explore with a light sail spacecraft. And to go further, what I told you about is essentially a phase one. And this phase one spent probably over a 7-year period, maybe $5 million. So it's sort of like one large DARPA project, maybe. It's not a lot of money considering the size of the ambition. And I think we learned a lot. I think I can say confidently there are audacious challenges, not all of which have been resolved. But we didn't identify anything that absolutely disables the notion of a laser-driven light sail spacecraft traveling over interstellar distances. And I think further work is going to require an international and multi-institutional group. Hopefully the world will still have some appetite for that with many scientific users and supporters. So thanks very much.
Wow. Okay. I have a lot of questions, but we'll start with the audience. How about Al?
Two short ones. One is you mentioned something like a kilobit of information would be sent back.
100 kilobits.
100 kilobits.
Yeah. That's.
What information would that be, and would it be an image like that?
Well, okay. So here, if we look at my chart, okay, there's the number of pixels. So this is of order 100 kilobits. Yeah. For the.
One picture.
Yeah.
Or, okay.
Yeah.
Second question. So that's sending in information back, but at some level, this is also potentially a messenger. For
right.
Interstellar people or something.
Okay.
So you thought about what kind of message?
Well, this is something that we can probably carry on this part of the conversation over the reception. So one of the questions is, what should you look for if you send a spacecraft? And one of the things you should look for is flashes of light coming back to the Earth, which is some other civilization sending light sails towards us.
Yeah.
So you mentioned that the primary cost driver, both for Kuiper belt or an interstellar is the cost of the lasers. But the acceleration time that you listed is very short. It's thousands of seconds.
Yeah.
What drove such a short acceleration time instead of, a day?
It has to do with just diffraction limited optics. I have an optical aperture on the Earth, this phased array laser. That is the farthest distance I can go and maintain a diffraction limited beam spot that doesn't overfill the light sail. When it starts to overfill the light sail, the propulsion efficiency falls off, right? Because a lot of optical power, the full width half max of the beam is now larger than the light sail itself. So that's really the consideration. If you had a larger optical aperture, you could propel it further. Sort of serendipitously, it works out that this impulse of about 1,000 seconds, so it's about a distance of it's about 2 million kilometers or so. So that's the distance you could go. Yeah. Yeah.
With the size of the light sail that you did your mechanical mode
simulations. Yeah, that was actually a full, I think 4-meter diameter. The actual multi-physics simulation. There's a NatureCom paper that does it at that scale. Yeah.
So it's meters.
Yeah. The experiments are on the micrometer scale, but the simulation work was actually done on the meter scale. Yeah.
Also, that they would have lots of higher order modes.
Yeah. Okay. So interesting thing. Okay. So what happens when you take a membrane and you spin it? So we spent a long time actually with John Satter, who's a nice, who understands nonlinear dynamics quite deeply. What happens is you get some small amplitude displacement of the membrane from the center towards the edge, and then finally very close to the edge, within a few percent of the 5-10% of the distance to the edge, then the amplitude grows. So that basically the edges flap so the tensile stresses stabilize the membrane and hold it flat or approximately flat. And we think it would be flat enough at least to make the propulsion stable, but the edges flap. So I guess that is what we found. We did study what would happen if you put a stiff hoop, a hoop stiffing element right at the edge to prevent the edges from flapping. So that costs you mass. We tried to think about fancy 3D printed structures we could make in the Kavli Nanoscience Institute that could make a strong but light, low mass density hoop. So those are ways that you could overcome that. But fundamentally, a membrane, most of it stays flat when you spin it and you let it just explore all its various modes.
Then the biggest problem would be how you make single crystalline high quality materials to the meter size membrane. That because if you have some defects, then a lot of these simulations.
Yeah.
No.
Well, okay. So I guess one thing we know, it doesn't have to be single crystal. In fact, the silicon nitride is amorphous. We can deposit very uniform amorphous layers. In fact, my colleague Richard Norte in Delft University has built light sails at the 50 millimeter scale and is testing them. So we are not the holders of the record of the largest structures. So I'm pretty confident we can do that. And frankly, if you end up with a defect that induces anomalous absorption, it will just blow a hole in that region of the light sail and heal itself. So I think. Yeah, I mean, this is why it wasn't our leading candidate, right? So.
One question, Gil. I was wondering, so like 4 light years, how much stuff you hit on the way?
Yeah, okay. So what you're interested in is what's the density of the interstellar medium in terms of molecular density and particles that could induce some irreversible damage. Yeah. Yeah.
There's a lot.
So believe it or not, I dug into this with people who study the ISM, and there are density fluctuations in the interstellar medium. And so the answer is actually not known within about 3 orders of magnitude. But you know, some things are just not known, right? There's no, how would we have measured it? But the answer is roughly a particle per cubic meter or something, or something like that. So, and that particle would likely be hydrogen. You know, most of the interstellar medium is going to be gas. Yeah.
So we have time for one more question because the wine is waiting for us. But the question from Dave.
Is there any demand either academic or commercial for sending small light sails around the Earth at 20% of the speed of light? If we're back in Tuesday.
Well, we actually had an audience from Blue Origin and Amazon, and we were sort of jokingly talking about sending packages back and forth to Mars, right? So to do this, you have to have a laser on the other end that would decelerate by radiation pressure. Otherwise, it would sail right by. But it's not a preposterous idea. No more preposterous than what I've told you before. And that you could design something that would slow it down as well as accelerate. Yeah. Yeah.
Well, I think people are aware that the moon landings spurred a lot of innovation, and that was just a moonshot. And this is beyond the sunshot. This is a real starshot. So, I mean, we all hope that it is going to succeed, but I can just tell there's going to be so much spin-off technologies from it.
Yeah.
And the number of people who get excited to work on it is, maybe the most important byproduct of all.
Yeah.
So anyway, I'm pretty excited about it. So let's thank Harry and join him for this.